The motion tracking sleeve is an innovative device that will revolutionize motion capture. The goal of this project is to create a virtual reality glove system that allows for position tracking and full range of motion. The product consists of sensors, 2 microcontroller units, an application programming interface, and demo applications. The sleeve measures the angles of each joint, from the fingertips to the shoulder, as well as its motion through 3D space.
The array of pods that are used to measure the angle data must be fixed to the joint they are measuring. By 3D printing special pieces for each joint, the pod body can remain static while the knob can rotate 180 degrees, varying the middle pin voltage from 3.3 to 0 volts. Linear pods are essential to the system and need verification. The initial DNL or max air for the pods was 24 millivolts or 1.3 degrees, and after 2200 turns of the pod it increased to 53 millivolts or 2.9 degrees. The initial INL or max value of some DNL values was 2.27 volts, and after 2200 turns of the pod increased to 3.29 volts. Here we see a power breakdown of the system. When hooked up to 3 AA batteries, the system draws 73.9 milliamps, which dictates the usage time to just over 20 hours.
Voltages from the potentiometers are read into the MSP onboard ADC. The SPI bus is used to communicate between the IMU, cap touch sensor, and secondary MCU. The UART bus handles transmissions between the secondary MCU and the host computer.
The Data Processing API handles connecting to the sleeve, unit conversions, and multi-threading. Multi-threading allows communication and processing to happen in parallel with the main application that uses the data. This ensures the computer application runs smoothly without stuttering. Here a test program uses the API to read a full set of data from the sleeve. This is done 100 times and the total duration is measured. As you can see, the average transmission time is less than 10 milliseconds per packet.
And go.
The first program takes triangulation data and maps it to mouse movement. The second program for the user application submodule takes the ADC data from the data acquisition submodule and converts it into degrees. This degree value is then mapped into one of the 27 hinge joints attached to the Unity model seen on screen. The model moves at a little over 60 FPS, so there is little visual lag, and there is not much delay between the movements of John and the movements of the Unity model.
And applications are not limited simply to a 3D model or a mouse program. The study of human motion brings vast amounts of knowledge to the robotics field, whereas the ability to precisely track movements would allow doctors to better analyze their patients and measure progress in physical therapy. It could even be taken into the video game industry to revolutionize virtual reality. By removing the field of view limitation, the possibilities are endless. It's our hope to create a product that can be used by developers in many fields and a wide variety of applications. We hope you enjoyed our presentation, and thank you for your time.